Hey guys, welcome to our very first lesson in our geometry course. This lesson is going to be about points, lines, and planes. When we're done this lesson, we're going to be able to identify and model points, lines, and planes. And we're going to be able to tell what happens when they intersect, when lines intersect, what happens, what do we call that? And when planes intersect, what happens, what do we call that? So let's take a look at our new vocabulary here. Our first term is this term called undefined term. And these are the fundamental building blocks of geometry: our points, our lines, and our planes. And we call them undefined terms because the only way you can explain them is by showing examples like this. So here's our point. A point it's a location in space. It has no shape, no size, but of course, if we didn't come up with a symbol to represent it, you wouldn't be able to see it or talk about it. So we give it a dot. We give it a little dot like that, and we label it with a capital letter. For instance, this would be point A. Now, if we take 2 points, between them, we could connect them with a line. We could draw a line. So if I had this point A and this point B, now we have a line. And a line extends infinitely in both directions. And to indicate that it goes on infinitely in both directions, we give it an arrow on each end because you can't draw something infinite. So we use those symbols to indicate that it keeps going. Now you could call this line AB. You could call it line BA. You could also label this line with a lowercase scripted letter. You could call this line L in this case. Now, if we move beyond 2 points and we add a third point that is non-collinear, and we're going to look at that term in a little greater depth in a second. But when I say non-collinear, this word, non-collinear, okay, collinear implies things that share, a line, collinear, things that share a line. Things that are non-collinear do not share a line. So I'm going to pick a third point that is non-collinear. In other words, I wouldn't put it here. I'd put it somewhere off the line, maybe somewhere up here, and call it point C. Here's an example over here. If we take 3 non-collinear points, then we've defined our next fundamental building block of geometry, the plane. Okay, and you can see A, B, C. If you were to connect these with line segments, you'd end up with a triangle. And if you decided to extend that triangle or those line segments, rather than making them line segments, let's make them lines and make them go on infinitely in all directions. And when you do that, you end up with what we call a plane, which is essentially a flat surface that extends infinitely in all directions. And if we wanted to name this plane, we could call it plane ABC. You could name it by its 3 non-collinear points. You could call it plane CBA, plane CAB, or you could label it perhaps more easily with an uppercase scripted letter. In this case, we're using letter P. We would call that plane P. Okay, those were our undefined terms. Now, we can use our undefined terms to create defined terms. Our defined terms, sometimes called our definitions in geometry, are our terms of geometry that we explain using the undefined terms point, line, and plane. And some of these definitions are collinear, which we talked about briefly in the last slide. Collinear are points that lie on the same line. Co implying that they share, line implying, well, linear implying line. They share the same line. If they're non-collinear, then they're not on the same line. Likewise, we have this term coplanar, which implies things that share the same plane. So this could be points or lines that lie in the same plane. Intersection when we talk about an intersection, we're talking about the set of points that two or more geometric figures have in common, or you might think of it more simply or visually as, where do they cross? If these were two lines, we would say they cross at their intersection. Now, if two planes cross, what do you get? Let's pretend this hand is a plane and this hand is a plane. And where they intersect, they form a line. Okay, so we're going to use that term intersection when we're talking about lines and planes. And then generally we're going to be working in space, which is a boundless three-dimensional set of all of our points, where we can work with points, lines, and planes. All right, in this problem, could we use this figure to name a line containing point N? Okay, now points are represented by dots and a capital letter, so you can see here we have point N. So if you wanted to name a line containing point N, you might say it's on line C. Okay, you could call that line C with this lowercase scripted letter C. But you could also use 2 points to name this line. You might call it line LN. Okay, and the symbol we would use to indicate that it's a line and not a line segment is we draw this line over the top with arrows pointing in both directions. That tells us that that is line LN. Okay, but there's other options here. We could also call it line NL. That would work as well. Don't forget your symbol over the top. We could call it line MN. Excuse me. We could call it line NM. So there's lots of options there. Could we use this same figure to name a plane containing point M? So these red lines represent this plane F. Okay, and we have to draw these red lines even though planes extend infinitely in all directions. If we didn't cut it off, we wouldn't be able to see it at all. So we represent it with sort of a shape that looks like a parallelogram, and we call that plane F. Okay, so that's one option. Let's see if I can draw a cursive F, see if I remember how to do that. So you could call it plane F, but you could also name a plane by 3 non-collinear points. So I could say LBN. That defines that plane. I could call it plane LBN, or maybe NLB. I could call it MLB. I could call it MBN, or some combination thereof. But I couldn't call it plane LMN. Why not? Those 3 points are collinear, and they only define a line. They don't define a plane. Those points don't tell me which way that plane is facing, okay? Because I can picture those as a line, as an axis, and I can just spin around that axis. It doesn't define a flat surface for me. But if I add this point that is off the line, that is non-collinear, now all of a sudden I've got that flat surface defined. I know exactly where that flat surface lies. Okay, here's a good opportunity to pause the video if you want to try a problem yourself before I explain it. Here, could we use the figure to name a plane containing point D? You can see here we've got this capital letter D and our point right there. So how could we name the plane that it's in? We could call this plane P, right? I could have that as an uppercase scripted P. Apparently, I don't remember how to draw a cursive P, but we could call it plane P. We could describe this plane with 3 non-collinear points. I could call it plane DCF, right? I could call it plane DCE or EDC. There's lots of different ways to name it. There's only one plane here, even though there's many, many different ways to name it. But there's only one plane here that we can see that contains this point D. Notice I couldn't call this plane D, E, F. Those are three collinear points. The best they can do for me is define a line. I can't define a plane. Could we name the geometric term modeled by a 6-foot by 12-foot platform? So there you might picture that as, if we were to try to attempt to draw this two-dimensionally, maybe we have a platform that's shaped like this, that's 6 feet wide and maybe 12 feet long. And you can probably picture when I draw that out that that looks like, it's not a point, it's not a line, that would represent a plane. Could we do the same thing? Name the geometric term modeled by a star in the sky. Now, if you were to look up at the night sky, you know, it might look something like this. And hopefully you can see, those might be a little tough to see at this resolution, but those tend to represent points, right? If you look up at a star in the sky, you're going to see a point. Now, if you were to try to imagine constellations, you could connect those points with line segments, right? Line segments, for instance, you might do something like that. If you wanted to extend that line segment on infinitely in both directions, then you would have a line. How about a dot on a map used to show the location of a city? If you ever seen a map, and maybe you've seen, well, this one might have a star next to it, you know, it might say Boston. But then if you look up to the northwest, you might see a little dot that says New Ipswich. And you could say, oh yeah, that dot represents a location in space. That would be a point. How about the geometric shape modeled by the window in your classroom? Well, if you were to look at your window, you'd probably say that flat piece of glass represents a plane. Okay. What about the edge of the window in your classroom? If you were to just look at the edge, now you can think of each corner of your window as individual points. Corner represents a point, lower corner, upper corner, and if you were to connect those points with an edge, well, that would represent a line. The actual edge is a line segment, but you could extend that on in all directions and say that it represents a line. All right, could we sketch a diagram that represents the situation that they're describing here? We've got a plane B that contains lines EF and GH, which intersect at point J. Point M is also in plane B, but it is not collinear with line EF or GH. Now, I recommend that when you have a problem like this, you read the whole thing once, and then you go back and just take it apart one piece at a time. So we've got a plane B. I'm going to go ahead and just draw myself a plane B. Let's do that. A little scripted B there, uppercase scripted B to label the plane. And we've got lines EF and GH, okay? Before I draw them, I'm going to read just a little more. They intersect at some point J, okay? So I know these two lines are going to cross, so I'm going to draw them that way. I'll draw this line, and I'll say it's defined by these points E and F. And it's going to intersect with this other line, GH. So I'm just going to draw a line that intersects it, that crosses it. Okay? And that line is defined by the points G and H. What else do we know here? Where do they intersect? They intersect at some point J. So I can go ahead and put a little dot down there with a capital letter J to represent that intersection. Now, point M is also in plane B, but it is not collinear with line EF or GH, excuse me. So Could I put point M here, or here, or here, or here? I can't do that, can I? Because if I did that, point M would be collinear with either lines EF or GH. I don't want it collinear. I do not want it to share those lines. So I'm going to place point M anywhere off those lines. I'll just put it right there. And that is one possible representation of this situation that they're describing here. Could we sketch a diagram that represents this situation? We've got line ST defined by these points S and T, and they give us these coordinates. Now, hopefully you remember that when we're given a coordinate for, let's say, a point A, we're given X comma Y, okay? If you ever forget, they're always in alphabetical order, right? X comma Y. So we could plot that on our graph, and they want us to graph the line and then place point V so that it is collinear with points S and T. Okay, so I'm going to go ahead and say that this is my y-axis. If you want to do this with a straight edge, you can, but you don't have to, you know. You just got to sketch it out so you can give yourself a picture and understand what it is we're trying to accomplish here. So I got point S at -1, 5. That's -1 in the x direction, up 5 in the y direction. 1, 2, 3, 4, 5. Okay, so there's point S. And I recommend for the rest of this class, we're going to be doing a lot of this. And it's really helpful to add the coordinates to the sketch because you may end up doing some algebra with them, calculating slopes and stuff. So put the coordinates right on there. And then we've got point T, which is at 6, -2. So that's x is 6, y is -2. I'm going to go over 6, 1, 2, 3, 4, 5, 6, and down 2. So here's point T at 6, -2. Okay, and you might want to give yourself a straight edge when you're drawing these lines. It doesn't hurt. And I'm using a rudimentary straight edge here. Okay, and I'm just going to draw arrows on each end because that's a line. It goes on infinitely in both directions. And what's the last thing they want us to do here? I always recommend you read the problem one more time before you send it. Graph the line and place point V so that it is collinear with points S and T. If it's collinear, then it's going to fall on this line that we just drew. And I'm going to go ahead and suggest that we could put point V right here on that line. It looks like it would end up at 2, 2. Good. Okay, you might want to pause the video and try this one on your own. This is similar to the last problem, just another example. Line BC is defined by points B, which I'm going to go ahead and plot B at 1, 2, 3, 4, and up 5. 1, 2, 3, 4, 5. There's point B. 4, 5. Good. And point C, which is at 0, -1. Okay, so there's point C. And I'll go ahead and use my straight edge to just connect those. And that's going to go on infinitely in both directions. So we'll just give it an arrow on each end to indicate that. Good. And they want us to place point K so that it is collinear with points B and C. Okay, well, I just got to drop it anywhere on this line. I could put it down here. I could put it right there. I could put it up here. I could continue on if I wanted and put it way out there. I'm going to go ahead and just put it right here. Looks like that's a good spot for it. Okay, looks like we're at, just graphically, I'm going to pick that off. We're over -1, 2, 3, 4. And we are down -1, 2, 3, 4, 5, 6, 7, -7. And that is our point K. There we go. We've just sketched that situation. All right, here's an interesting question. How many planes appear in this figure? And this problem introduces an idea that I'm hoping you can see here. Can you see this segment here? is dashed, that line right there, or that line segment, and that one too. What that's indicating is that these lines, this line comes down, and then this portion of it is hidden. Okay, so when you see a dashed line, that's hidden. What does that mean? It means it's going behind something, and we're going to represent it, but you wouldn't actually see it if you were looking at it. So in other words, this line isn't in this plane. It's coming down, and it's going through it. Picture this line going through that plane, if my hand was the plane. And you can't see the part of the line or the pencil that is below the plane, right? But on paper, we can draw it. We can draw it as a dashed line that continues on through. So what that's telling us is that line NM is in the plane. Line LR is going through the plane, and it intersects the plane and passes through at point N. Same thing with this line LM. It is not in the plane, it's going through the plane. It's coming down and hitting it and going through. And here's the part that we don't see because it passes under the plane, and then we see it coming out on the other side. So now the question is, how many planes are in this figure? Okay, well, we have one. We've got plane W, right? Are there any others? Remember, 3 points define a plane. And if LR passes through this plane, we could say N is in the plane, but points L and R are not. In other words, I could say there's another plane right here, this plane L and M. Okay, so we've got plane W, and we've got plane L and M. Now notice this question is asking how many planes appear in the figure. It's not asking how many different ways can you name the planes, because I could call this plane here LNM, NML, MLN. I could go clockwise and call it LMN. There's a lot of different ways to name it, but there's only actually 2 planes in this figure. Okay, using that same diagram, could we name the intersection of line LN and line LM? So LN and LM, where do they intersect? Where do they cross? Or what point do they share in common? Well, it turns out that those 2 lines intersect right there at point L. Now, do you remember what happens when 2 planes intersect? This is asking if we can name the intersection of plane W and plane L and M. Okay. Now, when 2 lines cross, they form a point. When 2 planes cross, they form a line. I don't know if you can picture that. If I take this hand and call it a plane, and this hand and call it a plane, and I make them intersect, what is formed where they cross? You can see a line forming where they intersect. And you can hopefully picture that where this plane crosses this plane, they are intersecting right here on this line NM. That line NM is formed where those 2 planes cross one another. So if we were going to name the intersection of plane W and plane L and M, I would say that is line NM. That's where they cross. Okay, how many planes do you see in this figure? And you might want to pause it if you want to try this one. This is like the last example. We've got this plane M, so there's 1, right? And we've got some uppercase scripted M there. What else do we have for planes here? Okay, you can see this dashed portion and this dashed portion indicate that these lines BF and CE go down through the plane. Okay, but this line AD appears to be in the plane. Okay, so it looks like this is forming a plane, and I could name it. I could name it with any 3 non-collinear points. So I can't name it AGD. That's just a line. That doesn't tell me where that plane lies. But if I were to pick a point that's non-collinear, maybe A, B, D, now all of a sudden I've defined that plane. We could call it plane A, B, D. So there's two planes. I see two planes in this figure. Now be careful. There's lots and lots of different ways to name this one plane that we just identified here. You could call it plane ABD, ABG, GBD, GCD, DCB. All of those are different names for the same plane. But there's only two planes in the figure. And could we name the intersection of lines BF and BC? Well, here's BF, here's BC. Where do they cross? And of course, a big hint is the fact that they share a letter, and those letters represent points. And we know when lines cross, when lines intersect, they intersect at a point. So point B is where these two lines intersect. All right, one last question for you guys. Could we name the intersection of planes M and BAD? We've got this flat plane M here. We've got this other plane that intersects it. We can call it BAD. Where do they cross? What is formed when two planes intersect? When two planes intersect, they form a line. And you could call this line where they cross, you could call it line AD. You might call it line AG or GA or DG or DA. Those are all different names for the same line. All right, guys, I hope you found that helpful. That's our very first lesson in our geometry course. We're going to use these fundamental building blocks all year long. So go back and watch this again if you need to. Try the homework. And if you've forgotten anything or if you've struggled with anything, come back and take a look at this, because this is going to form the foundation on which we're going to build the rest of this class. Thanks for watching, guys.